All right, this is a basic Atwood machine. In true discussions of Atwood machines, the idea is that we are comparing perhaps the weight on one side with the weight on another and discussing how the system behaves. In a real Atwood machine, the pulley would be part of the system as well, in that the pulley would have inertia. It's an important distinction for us in this class to split up this discussion. And first semester, our pulleys will have no inertia. And because they have no inertia, this next thing is important. Understand that you have to know whether your pulley has inertia or not to employ this next thing. If a pulley has no inertia, then the tension in any string used on it is the same throughout the string. That's only true if the pulley has no inertia. The pulley you guys used yesterday had very little inertia, but real pulleys are going to have inertia. And all that means is that they resist they resist acceleration. That's all it means. But if you played it all with the pulley that you had on your table yesterday, you notice it spun pretty freely. It didn't take much force to get it to move. It had very little inertia. Now, I think most of you understand how this system's going to behave. That if there's a heavier box on one side than the other, the system's probably going to rotate or spin in the direction of the heavier box. What we're interested in is how changing those weights affects what happens to the system. That's what we're interested in exploring. Now, the truth is, we use these systems all the time. A counterbalance system in an elevator is not uncommon. And so this, Atwood machines, I say, aren't real machines in that we don't exchange force for distance the way a other machine does, but the concept of an Atwood machine is used frequently. So I want to talk about modified Atwood machines because those are the ones that you're going to see more frequently, especially on the exam, or in practice. First, this next one I'm drawing is just a standard Atwood machine. It's just splitting up the pulley into two parts. What I have here is not a modified Atwood machine. It's just an Atwood machine. But instead of having one pulley and the weights on either side, I've just broken it up with two pulleys. This would be taking the track like we used yesterday and putting a pulley on each side of the track and hanging a string across it. So this would not be considered a modified Atwood machine. Now, to make it a modified Atwood machine, there. Now I have a modified Atwood machine. In this particular arrangement, there's only one box that's causing both boxes to move. So one box is supported on the table, while the other box is free to experience the acceleration due to gravity, or free to experience force due to gravity. So this one would be our first case of a modified Atwood machine. However, still no surprise, I think most of you realize this system would probably accelerate this direction, depending on how much friction there is here. Friction could hold the system in place, but there's certainly no chance that the box on the table is going to accelerate to the right. It's either not going to accelerate at all, or it's going to accelerate in the direction of the arrow. A modified Atwood machine. Another modified Atwood machine kind of look the same as the one we just saw, except in this one, box on the incline, box hanging off the edge. Modified Atwood machine, say M2, M1, some angle theta here. In this example, I probably wouldn't be able to tell you which direction the system would accelerate. There are too many possible variables. Even if there was no friction here, depending on the angle would probably determine some things and what the two masses are. There's probably angles in which it would accelerate this way, and there's probably angles in which it would accelerate that way. It would really depend on what that angle is. You guys follow what I'm saying? All of these represent different ways in which an Atwood machine problem can be presented. Here's what I need you to understand. The white boxes in these pictures, for the time being, represent the system. These are objects that are connected together and are experiencing a collection of forces. They are the system. Now, when I say system, I mean they are joined together in such a way that they will experience the same acceleration. All right? In all of these pictures, no matter what, one box can't move without the other box moving too. Agreed? And one box can't move at one acceleration while the other box moves at a different acceleration. Not if the string is going to be connecting them together. So in these, they are a system because they are joined together in such a way in which they will have to have the same acceleration. There are forces that are internal to this system, and there are forces that are external to this system. So no matter which one of these we choose, there are internal forces and external forces. The way you tell them apart, internal forces are third law forces that exist inside the system, meaning they act equally and opposite on the two objects. Those are third law forces act inside the system. They act equally and opposite on the objects. External forces act independently on the objects in the system, but affect the overall system. External forces act independently on the objects in the system, but affect the overall system. We don't consider the reactive force for the external forces on a system. We don't consider the reactive force for the external forces on a system. For example, I think most of you agree that there's going to be the force of weight acting on this box. It affects the system. I don't care about the reactive force, which would be the force of weight acting on the earth. I don't care about that. That's not part of the system. So when we talk about systems, internal forces are acting within the system. External forces are acting outside the system. So when we talk about a system, I will often name the objects that are a part of a system. Let's take a look at an example of this, what you're going to have to do to perform in one of these problems. And I'm going to use your lab as the example today. So consider the table. The cart that you had. and the weight that you hung off the edge of the system, or off the edge of the table. You had a very light, massless pulley. And we used some kind of light thread to connect the two objects together. So this represented our lab yesterday. We were establishing a system in which the car could accelerate for as long as it took for the mass to make it to the floor. And you attempted to measure the acceleration of those systems. Let's say that this is the mass hung, and this is the mass of the cart. Now, our multi-body systems are not going to be any different than the single-body systems. You're still going to do the same kind of analysis, which means you're going to draw free body diagrams and you're going to consider whether it's a first law problem or a second law problem. There are going to be a few differences, but not many. For the most part, you're just going to replicate what we've already done. For example, take a moment and draw a free body diagram. If you remember in your set of rules, it said you have to draw a free body diagram for each object in your system. So you'll draw 2 free body diagrams since there are 2 objects in your system. I'll wait a moment, then I'm going to ask some folks some questions. So you drew something that looks like that? Excellent. Excellent. I like it. Looks good. So, any questions about that one? Somebody else tell you about the mass hung? I should call something. Alex, tell you about the mass hung.
I had the weight going down and then tension going up, but the weight was greater than the tension.
As what?
Greater than the tension.
Okay. Anything else? I think that makes reasonable sense. Now, before we get into this, there's a few things about multi-body problems that are different. First, I know you're supposed to make a coordinate system and you're supposed to align that coordinate system with the direction of the acceleration. What I would encourage you to do is consider the role the pulley plays in most of these problems. For the time being, since our pulleys have no inertia, all they really do is redirect the direction of force. However, in your notes, consider the actual thing that's happening to the pulley. The pulley isn't just floating in space. There is something that connects the pulley to the table. You guys had a clamp of some sort that connected the pulley to your track, correct? There's actually forces acting on the pulley. And the pulley is a part of your system. We are just not considering it this semester. We're going to consider the forces on the pulley next semester. But truthfully, there's tension acting this direction on the pulley and tension acting this direction on the pulley. And there's probably something that attaches the pulley to the table that applies some kind of other normal force. This keeps the pulley in place. Net force on the pulley was 0 because the pulley didn't go anywhere. Now, next semester, we're really going to have to kind of deal with the pulley part of this. But this semester, we're only going to look at it in a cursory way. But I would like you to consider that what for the most part's happening is that the pulley is redirecting the direction of force. What I would do if I were you, and you want to try and get these kind of problems, head them off and get them right, is I would use the pulley as the place to dictate what direction you're going to make positive. I'm going to make this direction positive. What this is telling me is that there is a unified direction for positive between the cart on the table and the weight that's hung off the table. I'm using the pulley as the place to indicate that, but if I extrapolate the pulley, what I'm saying is that this direction is positive for the cart, and this direction is positive for the weight. A unified direction for positive. Your book does this different, and I don't like the way the book does it. I like this way. But if you want to see a different presentation, use the book's presentation. Now, since our pulley has no mass, the tension in the string is the same everywhere, which means this tension and this tension are the same. You can probably now begin to imagine that on your test, there's going to be a grid there. And you had better make sure the arrow that you draw for the tension on one of these objects is the same length as the arrow you draw for tension on the other object. Now, with that being said, you should be able to put together a Newton's law relationship for everything that's going on here. For example, net force in the y direction over here is 0. I'm thinking normal minus mcg equals 0. I'm also thinking net force in the x direction equals mca. I'm going to put a c there to remind myself that this is just talking about the mass of the car. Now, if I finish this off, I'll have tension equals mca. Good so far? Do the same thing for the weight that's hung. Write a Newton's law equation that would do for the weight that's hung. What's that? Yeah. Not MHG, though. MHA. And all we're doing here is, again, Newton's second law. Net force equals MA. When you did the lab, did the weight that you hung fall at the acceleration of gravity, as if you had dropped it? Or did it accelerate at the same rate as the car? You guys did this lab yesterday. Did the weight and the car travel at the same acceleration? So it's not a stretch to say that this A and this A have to be the same. Right? Because they were joined together. The string didn't stretch. Whatever the weight on the weight hanging off the table did, the car did too. Now, what I want you to do, or be able to do, is to take what we know about the weight hanging off the table and take what we know about the car and kind of bring them together. So that's what I want to do. Not like that. Let's move that to the side. And for the car, we had tension equals MCA. And for the weight hanging off the table, we had MHG minus tension equals MHA. Now, if you look carefully at this, do you notice that one tension is positive and one tension is negative? It may not be clear, but these represent the internal force to the system. It's what connected the two boxes together. They are equal and opposite in the system. They're causing one box to accelerate and trying to prevent the other box from accelerating. So they serve different functions inside the system, but they are an internal force in the system. There are external forces in the system. The weight of the box that was hung, that's an external force. It's external to the system. And the weight of the car and the normal force in the table, external forces to the system. These are the forces that can cause the system to accelerate because they're external. Only external forces can cause your system to accelerate. It was in the definition. External unbalanced forces. So only external forces can cause your system to accelerate. Internal forces join your system together. I'll say that again. External forces can cause your system to accelerate. Only external forces. Internal forces join your system together. Now you have your data for your lab, right? You took it out, sitting in front of you. Have it out and get a calculator. We should be able to predict what the acceleration was that we expected. And look, it says it right here. All we have to do is consider bringing the car and the mass hung together. Now, did we measure tension during the lab? Do you have any data related to tension in the lab? You have mass information, don't you? And you have the acceleration information, don't you? So what I want to do is I want to eliminate tension between these two. I can do it two different ways. I could do substitution, where I just do direct substitution, or I can add these two equations together. I don't know if you guys have added equations together, but you're about to learn. You line up the equal signs, kind of like I did, and you just add like terms. I have a negative tension and a positive tension. When I add those together, that's 0. I have a term that has MH and G in it, so there's no other term with that in there, so just add that together. So I just added the left sides of the equations together. And now I'm going to add the right sides of the equation together, and I have MHA plus MCA. Just another way to do substitution. If you do this process the way I'm instructing you to, you will always have some forces that will cancel out, the internal forces. And what you're going to be left with is something that is about external forces. Now, you guys are pretty smart, but you tend not to see things unless it's really put in front of you. So I want you to see something. I'm going to factor out A on the right side. I don't know if you will see this, but I'd like to try. Newton's second law says if you add up all the forces acting in your system, you can set that in equal to the mass of your system times the acceleration. If we look back at our picture, the only force that was external to the system that could do something was the weight. The normal force and the weight of the car were balanced. They couldn't cause any changes to the system. But this force could. It was unbalanced in the system. When I look over here, I see the one unbalanced force in the system, the weight that was hung. I see the total mass of the system. And I see the acceleration of the system. This is net force equals ma. In a multi-body problem, when you're solving for the acceleration, you will always see a point where there'll be the total mass of the system. That will always show up somewhere in your problem. Look for it. Now, if I want the acceleration, all I have to do is solve this for A. So I'm going to do so by dividing both sides by the stuff that's in the parentheses. And I'll get MH divided by MH plus MC, all times G. I know I moved the G from here to over here. That's just so I can kind of show off something. Notice that everything in here is just the masses. Can you guys see that? It's going to be some scaling value for G. The top is going to be in units of kilograms or grams, and the bottom is going to be in units of kilograms or grams. So everything in this parenthesis is unitless because I'm dividing out something like grams divided by grams or kilograms divided by kilograms. Let's consider your lab. Most of you hung 50 grams off the side of the table. And most of you started with the car by itself. We're a lab, so work this out. I get 0.891. You did the lab. Does this fit in with what your data was? Should be close. We didn't eliminate all friction, but we eliminated a lot. If you did enough of the lab, you should have gotten to a point where you had like 1,500 grams on the track and left your 50 grams hanging off the track. What was this acceleration? Is that in range for your data? When you had lots of weight on there, did it start getting smaller? I hope so. And did it stay in this range? If you're getting stuff outside this range, you are making mistakes. This should be the range of our problem. Now, would you agree that these two accelerations are pretty different? I mean, one's almost 3 times bigger than the other. Consider the mass that was hung for just a minute. Did its weight ever change? I don't think so. It was 50 grams for most of you. That's 0.05 kilograms. Using 9.8 as gravity, that suggests that the weight was 0.49 newtons. And that never changed. So if we look at the two different instances in the problem that we just talked about, in both instances, the weight hung was 0.49 newtons. But in one instance, the acceleration was 0.89 meters per second squared. In another instance, the acceleration is 0.32 meters per second squared. Which one of these must have had more tension in the cable? I mean, if I'm trying to figure out the tension, I'm asking you about which one of these had more upward force acting on it. Why? Why'd you say 0.32?
Because the cart weighs more, so it would be like pushing back on the weight.
You're going way outside the scope of what I'm asking. If I just look at these two numbers and compare them with these two numbers, how do I know the tension was more on the left than the right?
Slower.
It was slower. That's it. There must have been more upward force here than here. because the acceleration was less on the left than the right. You will need to be able to explain this kind of stuff using this kind of simple language. But the one that accelerated the least must have had a closer balanced force. If it didn't accelerate at all, the tension upwards would be exactly the weight. Accelerated a little bit though, so the tension had to be just a little less than the weight. Here it accelerated a lot more, so the tension had to be much less than the weight. We're not doing this in a vacuum. You guys should be able to tell me the tension in both cases. I know you don't think you know how, but it's already on here. You should be able to tell me the tension in both cases. It's right there. Do so. Find both tensions. If you look at what I'm asking, I'm saying to you, tension equals the mass of the car times the acceleration. It's right there. One time the car was 1,500, but the acceleration was 0.32. One time the car was 500, but the acceleration was 0.89. You will have to convert that mass to kilograms to put this in newtons. So 500 is 0.5, 1,500 is 1.5. So it looks like here I get a tension of 0.48 newtons. While here I get a tension of 0.445 newtons. I know they don't look much different, but the takeaway that you need to be able to explain is that when the car was heavier, it was harder to move. The system accelerated less, and there was more tension in the cable. Here, the car was easier to move. The system accelerated more, and there was less tension in the cable. This means the tension was not always constant in your lab. But they were close, weren't they? They weren't that much different. In fact, I'm not even sure that we could measure that much of a difference between them if we put something on there to measure force. They were close. And the reason they were close is because of something else that's right here. Just look closely at this relationship and you'll understand why they were close. The thing that was overwhelmingly big was this, right? That was 500 to 1,500, while this was small. We made it that way. Now, consider some possibilities here. You can have what we did, where the car was much greater than the mass that we hung. Under these circumstances, I think you can probably notice that G is going to be pretty small, because we'll have a big number in the denominator. Can you imagine what the reverse would be? What if I hung a lot of weight and just put a little bit of weight on the table? Like, what if I hung the car but put that 50 grams on the track? Would the 50 grams stay there very easily, or would it accelerate really fast? Yeah, it would just rip it right off the table, wouldn't it? Now, this range is important. I mean, it would get close to G if this were the case. Right? Because I'd get a number divided by something that's very close to the same amount. But it barely accelerates if the thing was much different in the other direction. If the weight hung was much less than the weight on the table. Taking a look at an equation like this and making an analogy for these kinds of expressions is something I'm going to need you to do for your next test. It's not always going to be easy. In fact, sometimes it's going to be tough. We're going to end there.